Hi, my name is Türküeylüleken, and today I will be presenting my graduation project titled Early Detection of Agricultural Pests via Camera Imaging to Reduce Pesticide Use and Labor Costs. So let's start with why this research is necessary. Agricultural productivity faces a massive threat from the insect pests, and the studies shows that despite modern farming techniques, we still lose around 20 to 40% global crops annually to these pests. And in financial terms, that would make around $220 billion every year. So also, currently, the industry relies heavily on chemical pesticides, which is over 4 million tons annually. And while it kills pests, it also disturbs ecosystems and poses significant health risk to humans, as identified by the World Health Organization. So there's an alternative as a manual detection, but spotting tiny insects in a massive greenhouse is labor intensive and prone to human error. So that's why we need a solution that is automated, accurate, and reduces the chemical reliance of the farmers, of course. So my primary aim of the project is to build an automated greenhouse pest detection systems that solves a specific engineering trade-off, which is the balance between detection speed and the classification accuracy, of course. So deep learning models are accurate but computationally heavy, or at least from my computer. But and also motion detectors are fast but not smart enough to know what they are seeing. So therefore, I proposed a dual-stage system architecture, which is I will show. So here, as I mentioned in the previous slide, there is EYES, which is my method one, which is the motion detection engine that I completed using C++ for high-speed event detection. We can say wake-up system. And as I mentioned in my previous slide, again, my brain is method two, which is the deep learning model using YOLO 11 for price classification, of course. And I separated this year into two parts, which is phase one and phase two. And in this semester, I will explain my phase one, which is the focusing on building and validating these two organs of the system independently, of course. I completed these two systems independently because my first idea was to be able to understand the base of two systems, which is the OpenCV library and deep learning systems, which is YOLO architecture. And while by running them independently, I also had the opportunity to compare them, which is um, I was able to see if the motion detecting system is fast enough or is the classification model that I used accurate enough, which I will show. I will talk about my pros and my cons, of course. I will not hide anything that I did. But first, I will start with my motion tracking engine. I put the outputs of both systems in there. So we will watch it first and I will explain what I did. So as we can see here, the algorithm works in three steps. First, I use the Gaussian blur to smooth out the sensor noise. Then I use the Mach 2, which is mixture of Gaussians, for the background subtraction. And this is for the system to learn the static background, like leaves, and isolate only the moving pixels, of course. And then finally, I implemented the Kalman filter, and I did that because I wanted to be able to predict the future state of the insect so that I can have a stable ID even if the pest momentarily stops moving or gets blocked by a leaf. And for the results of this module, as shown by the green bounding boxes, the system successfully filtered out the static leaves. I will open it again and locked onto the moving insects. And for me, the common filter successfully assigned the unique IDs, like ID1, ID2, to track individual movements here. And however, this test also confirmed a critical limitation, of course, which is the brain part. The system runs highly sensitive, detecting the tiny insects, of course, but it cannot tell us what the insect is. And this is actually important because we need to be able to figure out if the insect is beneficial or is it just a pest, so that we do not have to um, do unnecessary work done in the greenhouse. So that's why we need the second stage, which is the artificial intelligence, of course. Now I'm going to open the output of my artificial intelligence model. For my second stage, which is the brain, this part, I selected the YOLO 11 Nano architecture. And I choose the Nano version because it offers the best balance and speed, and it's the latest version, so makes sense. And to simulate a real greenhouse condition, I also applied data augmentation techniques like mosaic and scaling. And for that, I utilized a GGS-V1 dataset. It is called that. And I also put the link here. The dataset contains over 5,000 images, and there are 45 distinct classes of crops and pests, of course. I trained the model on Tesla T4 GPU because my computer couldn't handle it. I used Google Colab. And I also want to mention something. It is important to say that the dataset is treated as a flexible component in this research, of course, because I may or may not have find a higher quality or site-specific dataset, and I want to improve my models by training them on qualified datasets more and more every time until I get the best performance. But for my phase one, this dataset was the most qualified above everything that I ever put on my reports as well. And it may not come out as I expected, it might not come out as low, but it teach me so many things, as I will mention right now. So analyzing the performance, as we see here, the model achieved a mean average precision of 37.4. And this also, of course, seems modest, but the class-specific breakdown tells me something that I have to learn, which is the larger insects like bulb flies achieved a high accuracy of 86.3%, and tiny pests like white flies, which I need to find out, had the accuracy of 26.3%. So the lower score for the tiny pests is came out with the problem of like small object problem. And white flies often appears as like dense tiny clusters rather than those distinct big insects, which makes them very difficult for standard models to count individually. And since my model's output came out great than I expected, I also wanted to put it here, and I also wanted to explain my cons rather than hiding it. So this finding suggests that for phase two, we might need a density estimation or another qualified dataset only for whiteflies, etc. Now, I also want to explain something else. While I was training my model, I had the problem of overfitting. I firstly trained my model in 50 epochs, and I also want to show the figures as well to be able to classify it more. I trained the model firstly on 50 epochs. If you look at the graph on the left side, graphs on the left side, you can see that after the epoch 20, the validation loss began to increase. And this V shape was the sign of overfitting. And the model started to memorize the noise in the training rather than learning it. So for that, I implemented a early stopping strategy at epoch 18. And as seen on the graphs on the right, the optimized run captured the model weights at the point of maximum generalization. So that ensured the system is robust when exposed to new images and unseen data. And lastly, I can talk about my models generally. And I have validated the motion tracker as an effective wake-up trigger. Uh, um, that filter can actually seize the moving insects. And I can say that I validated the YOLO 11 model as a capable classifier for distinct species. Of course, as I said, I may or may not have find a great qualified data set again, and I might train it more. That's the part I will bring it in phase 2. And also in my phase 2, I have to do my system integration. I will combine these two models so that the C++ motion tracker runs constantly and only triggers the power hungry AI model when the movement is detected, of course. And this will significantly save energy, of course. And I will also, after I've done my research again, after I develop my models and after I implement them together, I will put them in an embedded device and I will test it in a real world latency or in an actual greenhouse, of course. And that will be all for my project. Thank you very much for listening.